Hello, I am Dr. Vijaya Kishore, professor in ECG department. So today we are going to discuss about the course digital image processing. So this is the distribution of the electromagnetic spectrum over various frequencies or wavelengths, whatever we can call. So out of these all wavelengths, we are bothered more about the visible range, that is extending from zero point 0.4 micrometers to zero point 0.7 micrometers. Apart from that, we have X-rays, both hard and soft ranges, ultrasonic, infrared, radio waves, etc. and so on. So these are the few basic concepts of the electromagnetic spectrum, and we will be limiting our entire discussion to the visible spectrum, where we can visualize the objects present in the images. Digital image processing. So first let us understand what is a digital image. A digital image is a two-dimensional light intensity function f of xy, where x and y denote the spatial coordinates and f at any coordinate value x and y will denote the intensity or gray level or brightness value, or in just simple words we can call it as an amplitude also. And if all these variables f, x, y are all discrete in nature, then we can call it as a digital image. Now, processing this digital image using a digital computer is what is called as a digital image processing. So this digital image processing is classified into three levels. One is a low level, mid level and high level. So low level is characterized by the fact that the input and output, that means before and after processing, both are images. And the second level, that is called as a mid level, is characterized by the fact that the input is an image, but the output is an extracted attribute, that is a property of the image or property of the objects present in the image, etc. So these properties are very useful for recognizing the objects present in the image that we are going to process. The last one is a high level, which deals with adding some meaning or assigning some label or identifying an individual object or a region which is present in the image which is under process. So in general, an image is composed of tiny elements, we call them as a pixel or well, or in more generally we call them as a image elements or picture elements. So whenever we represent an image, we used to use the word the pixel. So most popular is a pixel rather than the well. And these are the related fields where the image processing has a lot of potential, both in research wise and also doing projects and all these things. So it covers almost each and every of the latest technologies: artificial intelligence, computer vision, imaging devices, computer graphics, optical engineering, etc. and so on. Next, coming to the fundamental steps which are involved in the entire digital image processing as a whole, this is the block diagram where we can see that the first is the problem domain. So the problem domain means the scene that is to be captured as an image and which has to be processed. So before we want to process, we should have the digital image. So what we have to do? We have to capture that entire scene of the objects in the form of a digital image. So for this purpose, the first step is image acquisition. So here we capture the image, or we capture the objects present in the scene that is to be processed. So for this purpose, we require some sensors, and these sensors should have the capability of transforming the light energy into an electrical signal. So here we have to use a digitizer if the output of the sensor is not a digital output. So mostly the sensors will generate an analog output or a continuous output. So this has to be converted into digital form by using a simple A to D converter. And next step is the image enhancement. So this is basically a pre-processing step which involves highlighting only a specific object or a specific group of objects present in the image. So whenever there is improper or non-uniform illumination over the objects in the scene, then some side of some portion of the object may be overly visible. So those kind of objects can be pre-processed such that they are easily identified in the next steps. So an example for this is enhancement, image sharpening, smoothing, both in spatial domain and frequency domain come under this image enhancement. Next is the restoration. So in general, when we are moving through a vehicle and when we take a photograph, so generally we observe some shades behind the objects. So that is because of the acquisition error. So this acquisition error is why? Because we have captured the image while we are in motion. That is the camera or the array or the sensor, whatever it may be, it is in motion. So what happens? The originality of the object is lost. That means we get a degraded version of the image. So from that degraded image, we have to restore the original objects present in the image. So all these comes under image restoration. So this involves some mathematical concepts like algebraic approaches, mean square filters, etc. and so on. Next is the color image processing. So this entire concept is based on the color image. So the color image can be represented as a RGB image, and here we extract the color attributes, and of course we process the input data as the color data only. And the next one is the wavelets and multi-resolution processing. So this particular step is very useful for multispectral image processing, where we can represent an image in different degrees of resolution. Next is a compression, a well-known task we have seen in signal processing also, the same reason here also. But the only thing is, there the signal is a one-dimensional and here the representation is a two-dimensional. So compression need is the same, that is to reduce the size of representation and also to reduce the transmission bandwidth requirement. And next one is the morphological processing. Morphology means shape. So this morphological processing involves extracting the shapes of the objects present in the image that is under process. And next one is segmentation, and this is a very important step in the entire image processing. So this can be defined as the process of subdividing an image into its constituent parts or objects. So generally we have to recognize an object and we have to give some label or we have to give some meaning. So that task of automatic recognition of the objects present in the image under process depends upon this segmentation. Depends upon this segmentation. So the success of the entire digital image processing depends upon how effectively we perform the segmentation process. And next is the representation and description. So in general, the output of the segmentation process is what's called as raw pixel data, which has no meaning. So this step, representation and description, will assign a meaning to that one. Will assign a meaning to that one, depending upon whether those pixels describe the external characteristics or they describe the internal characteristics. If the interest is on external characteristics, then we call it as bound representation. And if the interest is on internal characteristics, then we call it as a regional representation. So these two representations are used to extract the properties or attributes. And the description part is the next step in the same block, subblock, where this description will collect the attributes. So we call them as a feature selector also. Descriptor is also called as a feature selector. So these features are used to discriminate or classify one group of objects to another group of objects. And finally, based upon these descriptors, we finally identify the object. So these objects are in the form of adding a meaning or adding a label to it. In addition to all these subblocks, there is another important block called as a knowledge base, which is very important for the entire digital image processing. So this knowledge base will hold the type of the application, the nature of the image, and also it controls each and every step. See, depending upon the application, we can apply all steps or only few steps. So that is decided by the knowledge. So depending upon the type of the problem domain, this knowledge base will assign the processing steps out of these. Next, and these are the elements of any image processing system. And here we can see there are 7 sub blocks, including a network. And in this, we can see the mass storage. This is a very important element in image processing system. So this mass storage consists of 3 categories. So one is temporary storage, which is provided by the system that is being processed itself. And the other form of this temporary storage is frame buffers. And the second category is online storage, where we frequently access the images, and this is driven by magnetic disk, optical disk, etc. And the third one is the archival storage, where we rarely access the data that is stored. So for this we use a compact disk, etc. and so on. And the computer depends upon the type of application and the image that we are dealing. So a simple personal computer can also be used depending upon the application. And similarly, the images are complex, say some satellite images, then we have to use a supercomputer and so on. And the next one is a specialized hardware. This is also called as a front-end processor. And this is the heart of this entire image processing system. So this processor holds the digitizer along with the IAL. So AL stands for arithmetic and logic unit. And next is the image sensor. This is the first step where we already discussed in the fundamental steps. So if the sensor doesn't have the capability of generating a direct digital output, so that will be transformed into digital form by this specialized hardware. And these sensors can be have different arrangements that we'll be discussing later. And next come with the hard copies. There are certain applications where we want to take a hard copy of the processed image. So these hard copies can be preserved in the form of a printout on a paper, or it can be preserved in the form of a compact disc written on a compact disc and read later when required. And the image displays. So these are the displays are just like a monitors or a TV monitors like that. And these are driven by the specialized hardware. So if it is a PC, we have a monitor where we have a graphic interface card, and this graphic interface card is driven by the specialized image processing hardware. And finally, we have a network connection, where in some applications we have to get the images from a remote location, process them, and again send them back to remote location. So during that time, this networking will be very useful. And the technologies which we have for networking are the broadband technology, another one is OFC, optical fiber communication technology. So the first step, the fundamental steps of image processing, image sensing and acquisition. The aim of this image sensing and acquisition is we have to transform the light energy into a digital image. And the principle involved is the incoming energy is transformed into an output voltage signal with the combination of the input electrical power and also the sensor material. So in general, the sensor output will be analog in nature. So we have to use a digitizer at the output of the sensor if you want to change the output of the sensor into a digital form. And you can see this. This is the structure of the sensor. This is the incident light energy, and this dark region is the sensing material, and this is the power input, and this is the power output, and this entire arrangement is in the housing. And here we have a filter. This layer is called as a filter. So the principle is this is the incident energy coming from the objects which are present in the scene. So with this energy and with this input power and with the property of the sensing material, this sensor has to transform the energy into an electrical signal. And this is a single sensor, and here the sensors are arranged in line. We call it as a line sensor, and here the sensors are arranged in the form of array. We call it as a CCD array. So depending upon the type of the sensor arrangement, we have a different type of image acquisition procedure. So this is a procedure to capture a 2D image using a single sensor. So here the film is mounted onto a drum and the sensor is mounted onto a lead screw where there can be a motion from left to right. So one time when the sensor moves from left to right, one line of the image which is around the drum will be scanned from left to right, and again we have to increment this drum by rotating one step, and again the same thing, sensor must be removed from like this. So like this we have to perform for the entire complete 360 degrees to obtain a 2D image. So here one image line will be scanned per increment of the rotation and also the linear motion from left to right of the sensor. And next is the second arrangement using sensor stick. So here there is no need for a rotation of a drum. Here we have only a linear motion. So the number of sensors which are arranged in line will scan the complete line, and just moving the sensor this way or this way will provide the second dimension of the image. And the next approach is using array sensor. So here we can clearly understand the formation of a 2D digital image. So this is a source of light, just like a cameras have a flashlight, and this is the object in the scene that is to be imaged. So the energy from the source will fall on this object. Depending upon the nature of the object, this energy will be either absorbed or it will be transmitted. So that energy is to be focused onto the image plane. This is the image plane where the sensor array is kept. So if you want to focus the energy exactly onto the image plane, then we have to use an imaging system, which is basically a lens here. Why? Because we are using light as a radiating source. So this imaging system, which is basically a lens, will focus the entire energy that is coming from the object onto the image plane where the sensors are placed. So these sensors are exactly placed at the focal length of the lens. So after formation of this, after projecting the energy onto this image plane, what the system does is it simply integrates. So the energy is incident on the surface of the sensor, and the sensor will integrate the amount of energy in a slow manner, and then it converts into a digital form. So finally we get analog output of the sensor, and in between we use a sweep circuit, and these sweep circuits will transform the energy into a digital format. The next type of arrangement for image acquisition is using array sensors. So here we have an illumination source. This source will radiate energy onto the object present in the scene that is to be imaged, and depending upon the nature of the object, this energy, light energy, will be either transmitted or it will be reflected. So this energy which is coming from the objects present in the scene is to be focused onto the image plane. So for this purpose we are using an imaging system called as lens. Why we are using lens? Because here the radiating energy is light, so therefore we use a lens. So this image plane is the plane where the sensors are placed, and this is exactly located at the focal length of the lens. And the principle behind this conversion or transformation of light energy into electrical energy is that, so these sensors which are present on the image plane, they will be having an incident energy on its surface. So these sensors will integrate that energy which is falling on its sensor surface and transform that into electrical signal, which is proportional to the light energy that is projected on its surface. And the sensor output is analog, and this analog output is transformed into digital output by using A to D converter or sweep circuits, and this is the final two-dimensional digital image. Next is a simple image formation model. So this entire formation in the earlier case that we have seen, we have a source of light energy and that is falling on some object, and that energy is again captured by the lens and focused onto the image sensors. So this entire process of forming of an image is a physical process. And in generally, the images generated through a physical process, they will have values proportional to the energy that is coming from the light source or a physical source. So this light source has a non-negative energy and also a finite energy, and this you can observe here. The f of x, which is the image function, it is greater than 0 and it is less than infinite, means that it is a finite value. And moreover, in the earlier case, we have seen that there are two components which are required for forming an image. One is energy coming from the source, and the other one is the energy coming from the objects present in the scene. So these two components, that is the amount of source illumination coming from the source, is what is called as an illumination component represented by I of xy, and the amount of energy that is coming from the objects present in the scene that is being imaged is what is called as a reflectance component represented by R of xy. So finally, the function f of xy is taken as a product of these two components, I of xy into R of xy, where I stands for illumination component and R stands for reflectance components. And coming to these limitations of this I, once again it is a light source, so therefore it will be having a non-negative or a non-zero value, and similarly it will be having a finite value. And the other one is a reflectance, where the limits are 0 to 1. 0 stands for complete absorption and 1 stands for complete reflection. And this energy which is coming and all these things, formation of illumination component, reflectance component, all these to be generalized in the form of a range. So for that we have taken some L minimum and I minimum, where L equal to I into R minimum values, and maximum is I into R into minimum values. So in general, this L minimum and L maximum is what is called as a grayscale, which will completely describe the total number of intensity values present in that 2D image. So in general, this is shifted to 0 to L minus 1, where L0 stands for black and L minus 1 stands for white or grey, and all the intermediate values are the shades of white from black to white. Next step, let us understand how this 2D image is formed. So generally we have an analog image, and from this analog image we have to understand the process behind of converting an analog image into a two-dimensional digital image. So here you can observe there are two definitions: digitizing the coordinates and digitizing the amplitude values. So image is f of xy. So f stands for the intensity or amplitude, and x and y stands for spatial coordinates. So in this image sampling, digitizing the coordinates x and y is called as sampling, and digitizing the amplitude values is called as quantization. So here if you observe, we have taken an analog image, and over this analog image we are considering a line segment AB, this one. This is a line segment AB. And now what we are going to do is, we are trying to plot the intensity values of all the pixels which are lying on this line segment. So here the background is white and the object is black. So generally we get a profile like this. We get a profile like this. So this is high value, that is from this point to this point, and from this point to this point we have a low value like this, and from this point to this point we have again a high value. But in general, because of the acquisition errors, this profile will not be so exact. That is the transition from high to low and the transition from low to high. So instead there will be disturbance from here, and similarly there are disturbances from this part, and similarly there are disturbances from this part. And this sampling concept is determined by the acquisition method we are using. And coming to the complete this, coming back to this, so this is the image and we have plotted it. This is the practical 1D profile of the intensities which are present on the line segment AB. And now first we are applying sampling. That means we have a horizontal axis like this. This horizontal axis is divided into samples like this, which are equally spaced, and against that each sample we are representing the value of the amplitude by a box. We are representing the amplitude value by a small box, a square. So here this diagram gives a complete picture. So here the horizontal axis is equidistantly sampled, and against each sample we have an amplitude value represented by a small square. So here we have we have changed the samples into integer values on the x-axis, but these amplitude values are still continuous in nature. So to convert that, we have to apply quantization. So here we are considering a scale of 8 levels. So black to white. Now what we do is we project all these values of the square values onto the scale like this. All the values onto the scale like this. And on the other side, that is on the other side, we have exactly the lines matching the levels. So we have the lines, horizontal lines, exactly matching the levels. But whereas on the left side, when we are projecting these squares onto this level, they are not exactly colliding with the lines, that is the levels. So they may be in between these two values or in between closer to our value, low value. So depending upon this projection, we assign the value based upon the vertical proximity. So here we are projecting the amplitude value onto the scale depending on whether it is closer to above level or below level. On the other side, we assign that value. So like this, we project all the values onto this scale, and on the other side, we assign the levels, either high value or low value for the projected value based upon the vertical proximity. So finally, this is the the one-dimensional digitized line AV segment, that is intensity values. Now we want a 2D digital image. So here we are able to convert only a single line into a single digital line. So this procedure has to be implemented from top to bottom, line by line over the entire image in order to obtain a 2D digital image. So this digital image looks like this. So you can observe this is a continuous image. Finally, you can see here we have the squares which are occupied completely or partially, something like that. But here you can see the squares will be completely occupied. So these shapes may not match, but still, just to understand the digitation process, we have shown this diagram. So after sampling, as I said earlier, we are able to represent an analog image in the form of a 2D digital image. So this digital image is composed of image elements called as pixels or pels. So one representation of this digital image is in the form of a pixel representation. This is a conventional coordinate system. Here we have y coordinate and this is x coordinate, and all these dots stand for the pixels. And since we have taken this as a m by n image and we are starting the origin from 0, so from 0 to n minus 1 and 0 to m minus 1 we have this image, and this image, this digital image, is of size m by n, m by n. So this is a coordinate representation of the digital image which we obtain after image sampling and quantization. And we have two more representations where the function f of xy is represented in the form of f of 0 comma 0 to 0 comma n minus 1. Again, this is m by n size. And f of 0 comma 0 represents a pixel at 0 comma 0, and f at 0 comma 0 represents the intensity value at 0 comma 0. And we have another representation in the form of a matrix where this is also similar to the above one, but the only thing is the representation there we have f of 0 comma 0 and here we have p of 0 comma 0. And after sampling, we are getting the samples both according to the number of samples line by line we are doing from top to bottom, from left to right. So the size of the image is determined by the sampling process, and the number of gray levels is determined by the quantization. So here m and n stands for the size of the image, and k is the number of bits used to represent gray level. So we have taken L equal to 2 power k, where L is the number of possible intensity values or the number of possible gray level values for the particular image. So the total number of bits used to store that entire digital image is given by m into n into k bits. And if you are taking a square image, then the total number of bits is given by n square into k. And these are some examples for different sizes to understand the same formula, that is m by n by k. So this sampling has the effects, two effects, when we are changing the size of the image, and similarly when we are changing the number of gray levels to represent the image. So the first one is the effect of varying spatial resolution. So here we have to define what is resolution. So the resolution is defined as a degree of discernible detail. So how effectively we can identify the objects present in the image depends upon the number of samples, and also it depends upon number of the gray levels or intensity values. So in the first case, we are trying to discuss about the effect of varying spatial energy, where we are changing the size of the image, keeping the number of gray levels constant. So here for this example, we have taken a flower image which is of size 1024 by 1024, and the number of gray levels is 256. So gradually we are reducing that to 512 by 512 to display columns. So when we are reducing, we have to delete the columns and rows to reduce the image, but we are not changing any gray levels. And the next what we are going to do is these sizes, that is 512 by 512, is stretched back to 1024 by 1024. Similarly, this is also stretched to 1024 by 1024, and similarly this is also stretched to the original size of this one. All the images which are first reduced in size are later expanded to the same size, like this. So here we can observe there is no much difference between this one and this one. But when we observe the difference here from this level, when the size is from say from 64, 32 and then something below that, here we can observe some square-like structures at fine values. So wherever there is a sharp detail, there we have a square value. So this is the effect of reducing the size of the image, keeping the gray level constant. So this size reduction, that is what is called as a varying spatial resolution, is what is called as, this is called as a checkerboard effect. It is called as a checkerboard effect. And similarly, the second effect is we are keeping the spatial resolution constant and changing the gray level from k equal to 0 to k equal to 7. So the effect is called as false contouring. So here we don't have any circle, something like that. If you reduce that, we have a shade like this, and there is some contours are seen. So this is because of the representation of the intensity values by the number of bits than absolutely required. So we are representing with less number of bits than absolutely required. So then this is the case of varying the gray level resolution. Next is the basic relationships between pixels, and this is very important for understanding the relationship between the pixels: neighborhood, adjacency, connectivity, paths, regions, etc. Neighborhood. So we have three different types. One is a four neighbor, diagonal neighbor, and then eight neighbors. Four neighbors, we are considering a pixel p at xy, and these are the coordinates of the pixels which fall in this neighborhood, and this is a representation of the four neighbors. Similarly, diagonal neighbors, these are the pixels which are diagonal to the pixel p which is located at xy, and this is the location. And the last one is the eight neighbors of p. So both combined, four neighbors and then diagonal neighbors, that is all these coordinates combined together, we call it as eight neighbors. And next important point is adjacency. So this adjacency is very important to understand the relationship between pixels or to establish a path between the pixels. So adjacency, we have again three types: four adjacency, eight adjacency, and m adjacency. So we can define four adjacency as two pixels p and q should having value from v. So this is the similarity criteria. Are four adjacent if q is in set 4. That means what? Q must be a 4 neighbor. Similarly, 8 adjacency, q must be an 8 neighbor. And for m adjacency, which we are calling it as a mixed adjacency, and these are the conditions: q must be in N4 of P, there is a 4 neighbor, or Q must be in diagonal neighbor, and then the 4 neighbor intersection should be having a null. Null in the sense there should be no common pixels for 4 neighborhood of P and 4 neighborhood of Q. So here this is an example to understand the concept of adjacency. So here V equal to 1 is given. That means we have to establish a path between the values. So first examine this one. If you are taking this is a value 0. So V is given as 1. So discard. And from here you take down. And from here what are the 8 neighbors? 1, 2, 3, 4 and 5. Out of these 5, this is 0, this is 0, this is 0. So we can simply discard. And then we can connect this by this. And we can connect this by this. And so on. Next we move to this location. Again these two are already connected, and therefore we can establish a connection like this. So like this we have to move from each and every location and come like this. So this is what this is 8 adjacency, based upon the 8 adjacency. Here there is a small confusion. Here we have two paths. One path is this way and the other path is this way. So this results in ambiguity with 8 adjacency, and this is eliminated by the M adjacency. So this stands for M adjacency, where we can see that all the 4 pixel values from V equal to 1 are connected. At the same time this path is eliminated. So that is what is M adjacency. And similarly, you can observe here, if there are two subregions, if you want to say them connected or adjacent to each other, then some pixel in R1 must be connected to some pixel in R2, depending upon the type of neighborhood that is given in the problem. Next, connectivity. So to establish connectivity, these two conditions are to be required. There should be some kind of adjacency between the pixels, that is some kind of neighborhood. It may be 4 neighborhood or 8 neighborhood. And similarly they should have a similarity criteria, means the values that are to be connected must be having the values from the given set V. And similarly these are some other definitions related to the same adjacency, connectivity, all these things. Subset 2, subsets S1 and S2, as I said earlier, here we have taken Ri and Rg. Instead of Ri and Rg we can also take them as S1 and S2. So some pixel in S1 must be adjacent to some pixel with the given neighborhood criteria. It may be 4, 8 or diagonal. And next is the path, which is useful for establishing boundaries when we discuss about segmentation. And a path is defined as connecting all the pixels which are in between the starting point and the ending point. So the starting point is here is xy, and the ending point is st, and all the pixels which come in between is x0, y0, with the last pixel as st and the first pixel as xy. So if the starting pixel and ending pixel is same, then we can call it as a closed path. And based upon this, another some related definitions are region. So we call a region is a connected set. That means, suppose for example, if you are considering this as an image, and all these points which are in this image should be connected to each other. That means they should exist adjacency and they should satisfy some similarity criteria. Then we can call this as a region R. Similarly, boundary. So for this region, a boundary is set of pixels which will have one or more numbers that are not in R. So in this case, if the image, entire image is itself taken as this one, then the pixels which lie in first row, last row, first column and last column. So these pixels will have partial neighborhood, and those are called as boundary for this image. If we have any object within the image, then the pixels which are in the region should have pixels which are not belonging to that region. So like this we have to understand a region and then a boundary. And these are some simple questions to understand the adjacency and the paths, etc. And this is one more question to just understand whether these two regions are 8 adjacent or not. Of course, this pixel is connected to this pixel, so it is 8 adjacent. And similarly here the same thing. This pixel is having value from V, and we have to examine the two get pixels. So these two are not 4 connected. And what's the connectivity that is there? Is 8 connectivity. So they are 8 connected, but they are not 4 connected. So therefore they are not 4 adjacent. And similarly, this is another question where the following pixels, the two regions of ones are disjoint. Disjoint why? Because 4 adjacency is used. So this is a common pixel, center pixel for these two to connect this one or to connect this one. So in this 4 neighborhood, what is this? This one, this one, this one, and this one. So these 4 neighborhoods, we are bothered about only these two pixels. Why? Because this is in region 1 and this is in region 2. If this pixel has a 4 neighbors which are having values from V, that is 1 and 1, falling in this 4 neighborhood, then we can call them as 4 adjacent. But this pixel doesn't have any pixel with the same value and which is under 4 neighborhood and which is falling in region 1 and region 2, etc. So it is not 4 adjacent. It is not 4 adjacent. Right. So the next relation is the distance measures, and these are the conditions where we are taking P, Q, and Z as 3 pixels. And this is another one where you can observe the distance as Euclidean distance defined by the square of the distance under root, and this Euclidean distance. So, for example, if D is less than or equal to some R, it encloses pixels in a circle. It encloses pixels in a circle. And next one is city block distance. This is defined as the absolute difference and sum of the two coordinates. And for this, pixels will form a diamond shaped value as shown here. So this is for D4 less than or equal to 2. And here you can observe for D4 equal to 1, they are again 4 neighbors. And the other one is the chessboard distance, where it is called as a maximum of the difference between the coordinates, and this will form a square in shape. And here we can observe that for D8 less than or equal to 2, this forms a square, and for D8 equal to 1, these are 8 neighbors. 1, 1, 1 are 8 neighbors. And another distance measure that we have is the shortest distance, that is the DM distance, and this distance is different from the other three distances which we have discussed earlier, because the DM distance depends upon the value of the pixels and also the pixels which are present in the neighborhood. But whereas these three will depend only on the coordinates. These three distances will depend only on the coordinates, but whereas the DM distance will depend on the pixel values and also the values of its neighbors, but it doesn't depend upon the coordinates. And finally, the mathematical tools that are used in the digital image processing. So this is also very important to understand the basic operations that can be applied onto an image, because most of the projects will be using these operations only. So the first one is array versus matrix operation. So we know what is a matrix. In general, an image is represented as an array, a two-dimensional array. So here we can see this is one image with a 2 by 2 and this another image. So the product is array product where we are performing pixel by pixel. So a pixel in this location and a pixel in the same location of the second image, we perform the product like this. But whereas a matrix operation, we perform like this for first element, and for second element we perform the product and sum like this. So generally for image processing, we have to use array operation only, which is to be performed by pixel basis only. And the next one is a linear versus non-linear operation, and here we can observe this is the input image and this is the output image, which is process image, and this is an operator. H is an operator, and some textbooks we take it as a T also. So here we have to check whether this operator is linear or not. So to check that, that has to satisfy this condition. We call it as a superposition principle, which involves additivity and homogeneity properties. And the other third operations is arithmetic operations. They usually four: addition, subtraction, multiplication, and then division. And how these operations are used, arithmetic operations, is we can use addition operation for enhancing the image, and the same addition operation can be used for noise reduction also. So here we can use that for noise reduction also. And similarly, the subtraction is another enhancing the operation. So this is used in mask mode radiography, that is in medical field. So where we have an X-ray image, and then we take live images after sending some material into that, and g of xy is f of xy minus this one. So we move that, and then finally we try to enhance like this. So we find the difference of this, and then we are trying to finding the plot. Similarly, this is another example where we can see this is a skull image, and this is the enhanced image using subtraction. And next is the other operation, shading operation or image multiplication. So these are used for correction of the shades, both the division and multiplication operations. And the next one is the set and logical operations, and these are from the basic mathematics. And here we can observe some examples. A union B is standing for the entire thing, and A intersection B, and A complement, and A minus B. So these are the basic operations. And similarly with this we have logical operations. So the basic difference is set operations involve only one set, but whereas logical operations involves two different images, and these are operations on binary images only. Both the set operations as well as the logical operations are binary images only. So here you can see this is a image, not image means opposite. Two images we have. We have a combination of AND, very common value, and similarly OR, similarly AND NOT, and XNOR, and so on. And next the type of mathematical tool is the spatial operations, which involves three categories: single pixel operation, neighborhood operation, and geometrical space operation. So single pixel operation, as I said earlier, G equal to H, G equal to H of F. So this is the input image, and this is the output image, and H is an operation. Suppose if any pixel in G is a function of only one pixel in F, and that too in the same location. Say for example, G of 0 comma 0 comma 0 is obtained as a function of f of 0 comma 0. So hope you understood this one. So a pixel in the output image located at 0 comma 0 is obtained by a pixel in input image f, which is located at the same location 0 comma 0. That means what? One pixel in output is function of only a single pixel in the input image. So this we can call it as a single pixel operations. So these operations can also be transformed into another form as S equal to H of R. So here we have taken R is the representation for input gray levels, S is the representation for output gray levels, and this is the transformation function which gives the relation between the input gray levels and the output gray levels. So here when R equal to 0, S is 255, and when R equal to 255, S equal to 0. So this is a mapping curve which can also be used in place of G equal to H of. And next is the neighborhood operation. So in the earlier case we have seen that in G the pixel depends only on a single pixel, but whereas here a single pixel in the output, this is G, let us assume, and this is F. So a single pixel in the output depends upon the pixel along with the neighbors. So this neighborhood can be defined as m by n, and that neighborhood can be stated as S, X, Y. So g of xy is a function of f of xy plus its neighbors. So whenever we compute the output value by a group of values, where those group of values fall in the neighborhood of xy represented by s of xy, then we call it as the neighborhood operation. And the third one is the geometrical spatial transformations. So here we have an affine transformation. In general, this is the equation used to transform. So this is the original coordinate v, and this is the transferred coordinate, and this is some operation. So this intensity interpolation will assign the values based upon the transformed pixels, and this is a transform, a well-known transform, that is affine transform. And here, depending upon the values of t, we can perform translation, we can perform scaling, or we can perform rotation of the input coordinates v and w. And these are some examples we can observe, and these are the matrices, affine transformation matrices. So depending upon, as I said earlier, depending upon this transformation matrix, we can perform several types of operations: rotation, shifting, translation, etc. and so on. And next is the image transforms. This is another operation where we can perform modification on the input image, but in a different way. So here we have to apply modification in frequency domain. So for that, first we have to apply a forward transform, and then we have to apply the operation, that is h or some r, and over that we have obtain the output of the transform. And since we have applied some modification, and that modification is to be visualized, so therefore we have to apply an inverse transformation. Again, that is back to spatial domain. So the modification or change is indirect, that is in frequency domain. And for this we have several transforms, and this is a generalized equation. This is a very generalized equation where this r and similarly this is inverse equation. This s, both are called as forward and inverse transformation kernels, and these kernels are separable if they satisfy this condition r1 into r2, and they are separable and symmetric if both are functionally equal. These are functionally equal. Okay, so an example is a 2D Fourier transform. And next is a vector and matrix operations. So these are mainly used for multispectral image analysis. And here we can observe this is a color image, which is called as a RGB color image. So this color image is called as a composite image. Color image is called as a composite image. Now every pixel will be represented as a vector, a small R component, small G component, and a B component. So the same thing we have done here. So Z1 stands for red component, Z2 stands for green component, and Z3 stands for blue component. So this RGB composite image is divided into three component images. So this is red component image, this is green component image, and this is blue component image. So every individual component image is a grayscale image. And if you want to obtain the original color value, which is a color vector, so that means the color pixel is a vector, and grayscale image pixel is a scalar. So if you want, we have to take the same value from different components. Then we get the color pixel value. So this location, suppose for example, if it is 0, comma 0, in this plane also we have to take 0, comma 0, and this is also 0, comma 0. So if f of x, y is the color image, then f of 0, comma 0 equal to f of 0, comma 0 equal to a vector where we have r of 0, comma 0, and similarly g of 0, comma 0, and so on. Similarly b of 0, comma 0, like this. So here we have represented them as z1, z2. If you are taking them as z1 of 0, comma 0, z2 of 0, comma 0, this one. So this is a red plane image, this is a green plane image, and this is a blue plane image. So these are the vector operations that we have to apply for multispectral. And finally, these are the reference textbooks that can be referred by the students. Further information can be obtained, and these are very available books in the library. Thank you. And for any queries, you can contact me.